Welcome back to AI Paper Podcasts, where we dive deep into the world of groundbreaking AI research. I'm really excited to continue our series on classic diffusion model papers.
It's a fascinating area, that's for sure.
Yeah, and this paper, Diffusion Models Beat JANS on Image Synthesis, it really was a game changer when it came out in 2021.
Well, absolutely. It was a landmark paper, no question about it.
So let's rewind back to 2021 for a moment. Back then, JANS, generative adversarial networks, they were ruling the roost in image generation, right?
They were. JANs were creating some pretty stunning visuals, but they also had a bit of reputation for being, well, a bit temperamental.
Yeah, I remember hearing stories about how difficult they were to train. And the images, while impressive, sometimes lacked that, I don't know, diversity.
It's true. Training JANs could be a real challenge. It was like trying to balance two forces constantly fighting against each other. And you're right, the images, while often visually striking, could sometimes feel a bit too similar, lacking that broader range of variation.
So that's where diffusion models came in. And it's still mind-blowing to me that you can start with pure noise and end up with these, like, photorealistic images.
I know, it feels almost magical, doesn't it? It's like reverse engineering the process of noise corruption.
Okay, so help me wrap my head around this. How do they actually work?
Imagine you take a perfect image and you start gradually adding noise to it, like little specks of static on a TV screen. Eventually, it becomes completely unrecognizable, just pure noise. That's the forward process.
Okay, I'm with you so far.
A diffusion model is trained to do the reverse. It learns to take that pure noise and step by step remove that noise to reveal the hidden image.
It's like training a neural network to be this ultimate noise-canceling machine for images.
Exactly. It learns to predict at each step what noise was added, and then it reverses that process to generate new images. You start with random noise, and the model progressively denoises it, unveiling the final image, kind of like developing a photograph in a darkroom.
I love that analogy. It makes it so much more intuitive. Now, this paper, it wasn't just about diffusion models in general, right? There were some specific things they did that really pushed the field forward.
Oh, absolutely. There were two key innovations that really stood out, and they really set the stage for a lot of the progress we've seen since.
Lay it on me. What were these big breakthroughs?
The first one was all about tweaking the architecture of the neural network itself. They were using something called a U-Net, which was already popular for diffusion models.
Yes, the U-Net. Those U-shaped diagrams in the paper are pretty hard to forget.
Yeah, they have a certain visual flair to them. But the key thing is that they experimented with some really clever modifications to that architecture.
So they weren't just using the U-Net off the shelf. They were like tinkering under the hood.
Exactly. Think of it like tuning up a race car. You have a good engine, but you want to make it even faster. They incorporated these things called big-N residual blocks, which help the model understand the global structure of the image better.
Okay, so they're giving the model a better understanding of the big picture. What else?
Then they added multi-resolution attention, which allowed the model to focus on different levels of detail at the same time. It's like a painter who can zoom in on the fine brushstrokes, but also keep an eye on the overall composition of the painting.
So they're giving it both the microscope and the wide-angle lens.
Precisely. And finally, they used adaptive group normalization, which gave the model even more control over the features it was learning. All these tweaks together, they really supercharged the performance, bringing diffusion models much closer to JANs in terms of image quality.
It sounds like they were really squeezing every ounce of performance out of that U-Net architecture.
They really were. But the second big innovation, classifier the guidance, that's where things got really interesting.
Yeah, I've heard a lot about classifier guidance. What's the secret sauce there?
Imagine you want to generate an image of, say, a sunflower. Classifier guidance is like having a separate neural network, a classifier, that's trained on noisy images and can basically tell the diffusion model, hey, add a little more sunflower in this area.
So it's like giving the model an art director who can nudge it towards specific types of images.
Exactly. It's this additional guidance that helps steer the model towards a particular goal. And here's the really cool part. You can adjust the strength of that guidance, something they called the scale.
So you can control how much influence that art director has.
Precisely. If you crank up the scale, you get images that are incredibly faithful to that category, like a sunflower that's almost indistinguishable from a real photograph. But you might sacrifice a bit of diversity in the process. It's like choosing between a photorealistic portrait of a sunflower or a more abstract, impressionistic painting of one.
It's a great way to think about it. So they've got these souped-up diffusion models with their UNet on steroids and this classifier guidance system. How did it all actually stack up against the reigning champion, the GANs?
Well, that's the million-dollar question, isn't it?
Did they manage to actually beat the GANs?
They did, and it wasn't just a marginal victory either.
Spill the beans. Tell me more.
They put these improved diffusion models through their paces on some standard image generation benchmarks, things like the LSUN and ImageNet datasets using various resolutions, and they aced it. They achieved state-of-the-art results, beating GANs on key metrics, including something called FID scores, which measure both the quality and diversity of the generated images.
So they were getting both better image quality and more diversity. That's impressive.
It really was. They even observed that while their diffusion models produced images of comparable quality to GANs, they seemed to capture a wider range of the data distribution.
So they were covering more ground, so to speak, exploring more possibilities within that data set.
That's pretty remarkable. But wait, wasn't there one more trick up their sleeve? Something about upsampling.
You have a sharp memory. They did explore combining these diffusion models with upsampling techniques to get even better results at higher resolutions. Okay, so walk me through that. How does that work?
Think of it as a two-stage process. First, they use a diffusion model to generate a smaller image. Then they use another model to add in all those fine details, essentially scaling it up to a larger size.
So it's like using one model to sketch out the basic composition and another to paint in all the intricate details.
That's a great analogy. This multi-stage approach allowed them to achieve even better fidelity at those higher resolutions, really pushing the boundaries of what diffusion models could do. And, this work really did have a profound impact on the field.
Yeah, we should definitely talk about the broader impact of this paper, but I think that's a great place to pause for now.
Sounds good to me. We can pick up the thread next time. It's amazing to think how much this work from just 3 years ago influenced where we are today.
Right. It's not like they just, won a competition. This paper really changed the trajectory of research in image generation.
Yeah, exactly. It laid the groundwork for these incredible models we have now, like DALL-E 2 and Stable Diffusion.
Those are both diffusion models too, right?
Yeah, and a lot of the techniques that made those models possible, especially the architectural improvements and classifier guidance, came directly from this paper.
It's wild to see how quickly things have moved. So thinking about where things could go next, you were talking about classifier guidance and how it needs those labeled data sets. What about situations where we don't have all those neatly labeled images? Can diffusion models still work?
That's a great question, and it's definitely a hot area of research. Researchers are exploring all sorts of techniques to guide diffusion models without relying on those traditional labeled data sets.
Okay, I'm all ears. What are some of these new approaches?
Well, one idea is to use clustering algorithms to make what we call pseudo-labels from unlabeled data. Imagine you have this huge collection of images, but you don't know what they are. Clustering algorithms can group similar images together based on their visual features.
So even though you don't have an actual label like cat or dog, you can still group images that look like cats together and images that look like dogs together.
Exactly. Those clusters then act as kind of stand-in labels, giving the diffusion model some guidance.
That's clever. So what else are they trying?
Another really exciting approach is to train a separate model that can tell whether an image is from the real dataset or if it was created by the diffusion model, kind of like a quality control expert.
So it's like having a model that can tell if a generated image is realistic enough, even if it doesn't know the specific category.
Precisely. And that feedback then helps the diffusion model get better at generating images that look authentic. These are just a couple of examples, but there's a lot of work happening in this area.
It sounds like there's a huge potential for using diffusion models in situations where labeled data is hard to come by. I mean, think of all the unlabeled images and videos and text and audio out there.
I know, right? If we can figure out how to effectively guide diffusion models without needing those traditional labels, it opens up a whole world of possibilities.
Well, let's shift gears a bit. One thing that comes up a lot with diffusion models is speed, or rather the lack of it. GANs still have a reputation for being faster at generating images. Is that something researchers are working on?
Absolutely. The iterative nature of diffusion models with those many steps of denoising does make them more computationally demanding than GANs. But there's a lot of effort going into speeding things up.
What are some of the strategies they're exploring?
One really exciting direction is to try to distill the knowledge of a multi-step diffusion model into a single-step model. Imagine being able to go straight from noise to a finished image, skipping all those intermediate steps.
Wow, that sounds almost too good to be true. Is that even possible?
It's definitely a challenge, and these single-step models aren't quite as good as the multi-step ones yet, but the early results are promising. It's a hot area of research. I wouldn't be surprised if we see some big breakthroughs in the next few years.
It's amazing to think that we might one day have diffusion models that can create these stunning high-resolution images almost instantaneously.
Right, and think of the implications for fields like graphic design, art creation, scientific visualization. It could be revolutionary.
Absolutely. Now, aside from speed, are there any other limitations or challenges with diffusion models that researchers are wrestling with?
One big one is the quest for more precise control over the generated images. Classifier guidance is great for getting the model to create images of specific categories, but what if you want to control more specific things, like the pose of a person or the lighting in a scene?
The challenge of fine-grained control. That's where things get really tricky.
It is. That level of control is still elusive, but there's a lot of exciting work going on. Researchers are experimenting with more sophisticated conditioning mechanisms, using attention mechanisms, even combining diffusion models with things like reinforcement learning.
It sounds like there's still a lot of uncharted territory when it comes to really mastering the art of controlling diffusion models.
Definitely. It's like we've given artists a powerful new set of tools, but we're still figuring out all the nuances of how to use them to create truly masterful works of art. And speaking of exploring those creative possibilities,
We've been talking about images this whole time, but what about other types of data? Can diffusion models work with things like audio or text or even video?
it's a great question, and the answer is yes. The fusion models are surprisingly versatile. They're already showing some pretty amazing results in audio generation. There's this model called DiffWave that can create some really realistic speech and music.
So it's the same idea, adding and removing noise, but instead of pixels, you're working with sound waves.
Exactly. And it's not just audio either. Researchers are starting to explore using diffusion models for text generation and even video generation.
It seems like this idea of gradually corrupting data with noise and then training a model to reverse that process, it's pretty powerful.
It is. And it seems to be applicable to a wide range of data types. Of course, each modality presents its unique challenges, but the core principles are the same.
This has been a fascinating deep dive into the world of diffusion models. It's clear that this 2021 paper from Dhariwal and Nickel, it really was a turning point.
It was. It really helped kickstart this whole new era of generative AI.
For those listening who want to dive deeper into the technical details, where can they find this paper?
We'll have a link to the full paper, along with the code and some additional resources in the show notes.
Perfect. And for those who are feeling inspired and want to experiment with diffusion models themselves, are there any open source implementations available?
Oh, absolutely. You can find implementations of various diffusion models, including some based on this paper, in those popular machine learning libraries like PyTorch and TensorFlow. There are even some really user-friendly tools and platforms out there that make it really easy to play around with these models, even if you're not a coding whiz.
That's fantastic. So as we wrap up this deep dive into diffusion models, what's one key takeaway you hope our listeners will walk away with?
I think the biggest takeaway is that diffusion models really represent a fundamental shift in how we approach generating data. They offer this more elegant, more principled alternative to adversarial training, and as we've seen, they can lead to some truly amazing results. It's a powerful reminder that sometimes the most elegant solutions are the most effective.
Elegance and effectiveness. What more could you ask for?
Oh.
Well, on that note, a huge thank you to you, expert speaker, for walking us through this fascinating paper. It's always a pleasure to pick your brain.
The pleasure's all mine. I always enjoy these conversations.
And to our listeners, thank you for joining us on this episode of AI Paper Podcast. Be sure to subscribe so you don't miss our next deep dive into the world of cutting-edge AI research.